Hey everybody, in this lesson today we're going to learn how to do some calculations with acids and bases. We talked about the other day how if it's an acid, hold on, I didn't get a pen yet. If it's an acid, the hydrogen concentration is higher than the hydroxide, and if it's a base, the hydroxide concentration is higher than the hydrogen. And what we're going to learn today is how to use their equilibrium equation and their equilibrium constant to do some calculations and compare them. When we compare them, we will then be able to tell if it's an acid or a base, or remember, if they're equal, then it is neutral. And the other thing that we're going to work on today is how to use those numbers, the hydrogen and hydroxide concentrations, to calculate numbers on a scale called a pH and then a pOH. You've probably heard of a pH because a lot of people have had to measure the pH of maybe a hot tub, a swimming pool, a fish tank, something along those lines, or they've heard about the pH of acid rain. But every solution that has a pH also has a pOH. And so we'll learn today how those are calculated and how those are used to classify something as acid, base, or neutral. So all right, let's get started. So when we were talking about what is an acid and what is a base, we had this equation, how water can essentially break apart to give a hydrogen ion and a hydroxide ion. And this hydrogen ion is usually kind of stick into a water molecule. So, sometimes you see this written as H3O plus 1. H3O plus 1 and H plus 1, pretty much same thing. If you have H plus 1 in a solution, then you're going to have it stick into a water molecule. It is a reversible reaction, as we can see right here. And so as a result, we can write an equilibrium expression. Now, this is a liquid. Remember, we don't include liquids. We only include aqueous and gases because they can change their concentrations in the expression. So we have the hydrogen ion times the hydroxide ion, and there's nothing on the left side, so there's nothing on the bottom. And that would be equal to the KEQ, but they give it a special name instead of KEQ. They call it KW because this is the equilibrium expression for water. And the value is always at room temperature 1.0 times 10 to the negative 14. Remember, it's a constant. It is always the same at any given temperature, which was proven by Goldberg and Wage. We talked about that in the last unit when we talked about equilibrium. So this gives us an equation that we can use to solve problems, and let's give that a try. It says here, determine the concentration of hydroxide ions in a solution with a hydrogen ion concentration. There, we're given one. How might they know the hydrogen ion concentration? You can get that from the concentration of, how many moles of hydrogen are dissolved in how many liters of a solution. And so then if we want to know the hydroxide concentration, we know that this equation is true. And we would have to solve this equation for the hydroxide concentration by dividing both sides by the hydrogen ion concentration. And you can see that over here it cancels. And the only thing on the right is the hydroxide ion concentration. And that's going to be equal to the value of the KW, which at room temperature is always 1.0 times 10 to the negative 14. If the temperature is different, if the temperature is different, you can, look that up on a chart, what the KW value is. We're going to do all of ours at the solution's at room temperature. It's not hot or cold. And we're going to divide by the hydrogen ion concentration. Now, one of the things here is that you're going to have to remember how to use that EE button or the EXP to do the, powers of 10 on your calculator. Okay. So give that a try. And you should get when you solve this one. And then that's the label for molarity. So now we know that the hydrogen is equal to 1.0 times 10 to the negative 13 for its molarity. And the hydroxide is equal to 1.0 times 10 to the negative 1 molarity. And we can easily compare those. This hydroxide number is much larger than the hydrogen number. And going back to previous lessons, we know if the hydroxide is bigger than the hydrogen, this solution is a base. Okay, so we can classify this as a base by comparing those two concentrations. You can see that the only time that these two numbers, this one and this one, would be the same, they would both be 1.0 times 10 to the negative 7. That's the only situation that would be neutral. That 7 might be sounding kind of familiar in that 7 is neutral on the pH scale. And we'll show you how that is calculated. So pH for a solution is calculated by taking the negative logarithm of the hydrogen ion concentration. Every solution also has a pOH. The P stands for like potential, how many free hydrogens, potential, how many free hydroxides are floating around in this solution. And to get the pOH, you just take the negative log of the hydroxide ion concentration. When you get these two numbers, the pH and the pOH, because the exponents always equal 10 to the negative 14, these numbers are always going to, when you add them together, equal 14. And you'll see that in some math we're going to practice here in a minute. One of the things you maybe want to do is on your calculator, try and locate that logarithm button, okay? And many of you, if you don't have it on your calculator, your phones are sometimes more advanced than your calculators, even though I can't let you use them for quizzes and tests. But you can probably find that logarithm button on your calculator on your phone if you don't have it on like a scientific calculator to use to solve problems. The scales will look something like this. 7 is always neutral. On the pH scale, the low numbers are acid, with each number representing a factor of 10. So if I have something that is pH 6 and another solution that's pH 5, the solution that's pH 5 is 10 times more acidic than the solution that is pH 6. If I have something that's pH 4, it is 100 times, 2 factors of 10, more acidic than something that is pH of 6. Now, rain is naturally just a little bit acidic right in here because water reacts with carbon dioxide in the air to make carbonic acid. Rain is naturally a little bit acidic. Whoops, I didn't mean to draw that. Okay. But what happens is that, I've seen situations where the acid rain is measured like pH 5, and people say, well, that's not that low. That's 100 times more hydrogen ions than in a neutral solution. I've seen where they measure maybe a pH down close to 4 for acid rain. And again, people will say, well, that's not that low. That's 1,000 times more hydrogen ions than in neutral water. So please recognize that every factor on this scale represents a power of 10. And as you go this way, of course, that means that they are 10 times more basic. Now, there's also the pOH scale. Notice this time the low numbers are base. Look, last time the low numbers are acid because it's H. This time the low numbers are base because it's OH. But 7 is still neutral in the middle. Okay? So how can we do some calculations to help us to classify? And I see that my slide, the beginning of the question, it says calculate the following for this solution and classify as acid, base, or neutral. I see that kind of went off the top, so I'll fill you in on what that actually says. So here we learned earlier that if we want the hydroxide, we take the Kw divided by the hydrogen. So I'm going to take the Kw, which is always this number, it's a constant, and I'm going to divide by the hydrogen to get the hydroxide answer. Again, you should practice this on your calculator. And if you have any problems, email me. We can work out like a Google Hangouts, to help you figure out how to use your calculator. And I got 3.33 times 10 to the negative 6. So you want to try to get that on your calculator. Now, right there, I can pretty much figure out that this is a base. Does anybody see why? You see that 10 to the negative 6 is a bigger number than 10 to the negative 9. And if the hydroxide is bigger than the hydrogen, it's a base. Now let's see if that's what we get for the pH and the pOH on the scale. They also say base. Remember, the pH is the negative log of the hydrogen ion concentration. So I know my calculator, which is a TI-30X. I have to, I'll just tell you, I got to put this number in, then hit log, then hit negative. But I know that's kind of odd. A lot of the other calculators, you plug in the negative, the log, and then you put this number inside of the parentheses. So you will maybe have to experiment with your calculator to see how you do this. And again, if you need help, we can do a Google Hangout. But I got 8.5 for the pH. Now, if we go back to that pH scale, 8.5 is up here above 7. That agrees that this is a base. For the pOH, it's the negative log of the hydroxide. So I got to take the 3.33 times 10 to the negative 6, find the opposite of its log, and I got 5.5. Notice that these two add to give you 14. And that should always be true. We also got a pOH that's below 7. And we said that anything below 7 is indeed a base. So that agrees. And we now see that, yeah, this solution is a base, and we've fully described this solution. We know its hydrogen ion content, its hydroxide ion content. If we want to neutralize this solution, we know how much more hydrogen we need to add to neutralize the base. We know the pH, so we might know, whether the fish will live or die, whether the pool is going to grow, algae or bacteria. So, well, that's very odd. See if we go back to my presentation. Ugh. Now we're back. Whew, that is the first time that has ever happened to me. But now we fully describe this solution. And so people who take care of pools, people who take care of fish tanks, etc., these are numbers sometimes that they have to know so that they can work with that water solution and adjust it to have a proper pH. So let's do another one. This one, for some reason, that other one, the beginning of the question was off of the slide, but this one, it's good. So calculate the following for this solution and classify it as acid, base, or neutral. Okay. So here we're trying to calculate the hydrogen. So we got to take the Kw and divide by the hydroxide this time. So it's always 1.0 times 10 to the negative 14. And we have to divide by the 8.2 times 10 to the negative 4. And this is supposed to be a 14. Hopefully you can see that. So 1 times 10 to the negative 14 divided by 8.2 times 10 to the negative 4. And I got, for the hydrogen ion concentration, 1.22 times 10 to the negative 11. Man, sometimes it is hard to write. Now, we can see that the hydroxide is a lot bigger than the hydrogen. So we're going to say base again. I bet you thought if I gave you two problems, one would be a base, one would be an acid. But, this one also happens to be a base. Okay. So the pH is going to be the negative log of the hydrogen. So I got to calculate that. So let me calculate that. And I got 10.9. The pOH is negative log of the hydroxide. So, and that's going to come out 3.1. Remember, once again, look, these two add to give you 14, right? Add them together, you get 14. And again, it verifies base because it's got a low pOH, which is a base, and it's got a high pH, which is a base. Notice here the difference. This is an even greater difference than that last problem. And that's why the pOH was even lower. This is more basic than the previous solution that we looked at. So hopefully after this presentation, you can use that equilibrium constant, the Kw, to calculate the hydrogen or the hydroxide. Yeah, you have to have the hydrogen to calculate the hydroxide. You got to have the hydroxide to calculate the hydrogen. Once you have those, you can calculate the pH and the pOH, and you can compare the numbers to classify any solution as an acid, base, or neutral. So good luck. And, practice the calculations. Contact us if, oops, I wanted to say stop sharing. So contact us if you need help with using the calculator. This is definitely one where I like to see you in school and be able to help you out with the calculator, but unfortunately we can't, but we can meet virtually if needed. So good luck.